we are now going to move into the second part of this topic, but just a quick recap of what we have seen so far. Okay? We have started by arguing that we want to learn about relations between variables in the population out there that we do not observe, and that we are going to use the data to learn about the population. But the data is not sufficient. We also need a way of converting the data into our learning. We need a way of converting the data into our guesses about this population relation, into our estimates. Okay? This method or estimator, okay, should hopefully allow us to learn as much as possible. We have described a method or estimator that does that, the OLS regression estimator. Now the next steps are going to be to explain why that estimator is good and when that estimator is good. In other words, okay, we need some type of rule, some type of method to turn the sample into an estimate of beta naught and beta 1. We have used the method or rule of the OLS estimator that you have as formulas out there, okay, that we have seen several times already by now. And we have argued that this OLS estimator is good because it provides good guesses. It allows us to learn a lot. Okay? What does it mean that it provides good guesses? Well, that it has a number of good properties. So these good properties are statistical properties of the estimator. These are features that a method that we have to learn from the data should have. Okay, and we are going to see later that these properties are good, but only present if certain assumptions are satisfied. The first thing that we need to understand about why these properties are statistical properties, okay, is that the estimators are random variables. It's a bit strange to think about estimators of random variables, but they are. Okay? Now remember that beta naught hat and beta 1 hat are functions of the random sample. We have here, okay, the formulas, but these formulas are going to be fed, okay, with the data that comes from our sample. If the data has certain values of xi and certain values of yi, well, the estimate will be higher or lower or whatever. Okay? It will vary. So these estimates are functions of the random sample. If they are functions of the random sample, this means that they themselves are random variables. And random variables, we saw on the first day, on the first topic, have probability distributions or density functions, cumulative density functions, whatever, with their statistical properties. Okay? Let's see this graphically. Remember that we had a population relation. The population relation generated a certain population. Okay, so here's the population. Out there in the world, there is a very large, okay, maybe close to infinite number of individuals with the values of x, the value of y. We can observe them all, but we know that they are out there. So we are going to sample some of them. How are we going to sample them? We're going to sample them randomly. So here is, for instance, one potential random sample. Imagine that we happen to select these 4 individuals. Okay? Well, if we had these 4 individuals and we run a regression, that is, we fed these 4 data points into our OLS estimators, we might end up with an estimate, a prediction about the slope that takes, say, a value something like that. Okay, a pretty high slope. So let's put down, okay, this very high value of the slope here in this line at the bottom. But imagine that instead of selecting those 4 values here earlier, we have selected, okay, randomly by chance, different values to be part of our sample. Well, on the basis of these other 4 values, we might end up with a different estimate, because these 4 values, when being fed into the same OLS estimators, into the same OLS formulas, might have generated a different estimate, an estimate that is of a lower slope, of a flatter slope. Let's put it here, okay, to the left of the previous one. Okay, so this beta 1 hat double star is to the left of the beta 1 hat star that we had earlier. If instead we had selected okay, these other 4 values, we may have ended, okay, with OLS estimates that take this other value. In this case, the estimate is actually negative, a negative slope, say even smaller, even more to the left, okay, beta 1 had triple star. So you can see how, depending on the chance that we have in selecting certain values or others from the population and feeding them into our OLS formulas, we end up with different estimates. That is, our estimates are going to vary randomly. Well, if they are going to vary randomly, they are a random variable, and we can think of this random variable having a certain distribution. Okay, so for instance, this could be the distribution of this estimator beta 1 hat. So this estimator that has a certain distribution, well, this distribution may have a certain set of properties. We are going to see in the next section, not just now, but in the next section. Let me just at this point enumerate them without explaining them. We are going to see that statistical property number 1 is that the OLS estimators are unbiased estimators of beta naught and beta 1 of the population relations. We are going to see in statistical property number 2 that the variance of the OLS estimators follow these formulas that you can see in there. And lastly, we're going to see in statistical property number 3 that sigma hat squared, that we'll define later on in the next section, is an unbiased estimator of the variance of the error term. Okay, but now these statistical properties that we will explain and define later on are critically only going to be present under certain assumptions. That is, if certain things about the population are true. So now we're going to describe what these assumptions are. That is, when we see that the OLS estimator has these good properties, we're going to describe the assumptions that are necessary for OLS to generate these good properties. Statistical property number 1, 2, and 3. And here are the assumptions. Number 1, that the population relation is linear. Number 2, that the sample is random. Number 3, that there is variation in the variable x. Number 4, that the error unconditional mean is 0. Number 5, that the error conditional mean is 0. Let's study them one by one. But actually, let's go first to, not in order, but instead, let's study first number 2. Okay? Assumption 2 is that xi and yi that we have, okay, the individuals that we have selected to be part of our sample, okay, are a random sample of the population generated by, this population relation in there. In other words, it is random because the probability of being part of the sample is equal across units of the population. For instance, here we have a population that has been generated, okay, by this formula there, and every point in this population has the same chance of being selected to be part of the sample. Okay, for instance, we might select randomly these 4 points, or randomly these other 4 points, or randomly these other 4 points, all of them with equal probability. It is not more likely that we select these points than these points than these points, or so. Okay, all of them are equally likely. This means that the sample is perfectly random. Now, of course, on the basis of whatever sample we generate, we will end up with a different OLS regression line. The second assumption that we are going to describe, the assumption number 1, is that the population relation is linear. Actually, we have an assumption that we have already seen. We wrote the population relation being linear, okay, as having a constant slope in the relation between x and y given by beta 1. Remember that we just said that y is a dependent variable, x is the independent variable, epsilon is the error term, okay, and the parameters linking x and y are beta naught an intercept, and beta 1 a slope that is constant. The partial effect delta y over delta x is always the same, okay, certain parameter. So here it is. The population relation is linear. It's a line. We have the intercept beta naught, the value of y when x is equal to 0, and we have a constant slope beta 1, okay, that links the relation between the two variables. We said, of course, that typically x is not the only thing that affects y. Okay, so if x was the only thing, then we will observe every individual on top of this line, but x is not the only thing that determines y. We observe something different. Okay, and this higher or lower value of y, given what x will predict, is a result of the fact that there are other things that affect y. We put together all these things in the basket epsilon. For instance, in the case of observation number 4, epsilon 4 is positive. Assumption number 3 is that there is variation in x. In other words, the variance of x is positive. This is intuitively very easy to understand. Imagine that x did not vary in the sample in the population. If that was the case, it would be impossible to study empirically how y changes as a result of a variation in x, because we never observe x changing. Graphically, this is very easy to see. Look at this graph. Tell me whether intuitively x or y, y increases or decreases when x increases. Well, from these data points, it's impossible to tell. Okay? It's impossible to tell what will happen to y if x was to increase or decrease, because x never, graphically here, increases or decreases. If we have a little bit of variation in x, okay, if the variance of x is not 0, as in this case, but instead positive, as in this case, now we can start to draw some visual conclusions about the relation between x and y. For instance, we may say, well, in the basis of the evidence that we have visually, we will expect some type of negative relation. If instead there was still some variation, but of this other type, we will reach a different conclusion, certain positive variation. Assumption number 4 is that the unconditional mean of the error term is 0. Okay? The expectation of the error term is 0. Okay? Mean, okay, expectation, error term, epsilon. Unconditional means that we are not conditioning by anything here. This means that on average, before we know the value of x, we expect epsilon to have value 0. Okay? We say that epsilon, okay, is the basket, the set of other things that are not x and affect y. Okay? So epsilon brings the value of y above or below what the population relation by itself will predict. Okay? If epsilon is positive, then y moves up, okay, above the red line. If epsilon is negative, then y moves down below the red line. Okay, so here we have, that there is one potential value of epsilon for the first individual, a second potential value of epsilon for the second individual, another for the third, another for the fourth. Let's just think of all these as being, identical to each other, okay, generated, okay, in a very generic way. Let's refer to this as epsilon, just generally, epsilon. Okay, if we don't know anything about the error term, on expectation, we expect that some people will be lucky and their epsilons will be positive. Some people will be unlucky and their epsilons will be negative. On average, on expectation, the value of epsilon will be equal to 0. This is what assumption 4 tells us. On expectation, some people will be lucky, so they will be above the red line. Other people will be unlucky, so they will be below the red line. But on average, the value of their luck, the value of other things that affect y and are not x, is equal to 0. Okay. Assumption number 5 is that the conditional mean is 0. Okay, that is that the value of the value of epsilon for every value of x, even knowing the value of x, the value of epsilon is 0. That is, assumption 5 says that we expect epsilon, the error term, to have the same value regardless of the value that x takes. That is, the conditional mean is identical to the unconditional mean, the first equality that you have in there. The expectation of epsilon conditional on x is equal to the expectation of epsilon. We know from assumption 4 that the expectation of epsilon is equal to 0, or we assume from assumption 4 that the expectation of epsilon is equal to 0. Now, there are a number of immediate implications from this assumption. That is, a number of things that are true if this assumption is also true, which is that on expectation, y is equal to beta naught plus beta 1 times x, because conditional on x, epsilon is 0. Something else that is true under assumption 5 is that epsilon and x are not correlated to each other at all. They are perfectly independent from each other. Their covariance is 0, or the expectation of their product is 0. Okay? What does this mean? Now, we have here, okay, a certain probability distribution, okay, or density function that had a 0 mean. Well, the fact that the assumption that the conditional mean is 0, okay, means that the mean of epsilon is 0 for the first individual with a low x, for the second individual with a slightly higher x, for the third individual with a slightly higher x, for the fourth individual with a very high x. So we expect epsilon to take 0 value not for a generic individual, but for every individual independently of what the value of x is. That is for individuals with a low value of x, but also for individuals with a high value of x. Okay, so what do we need this assumption for? We are going to see that assumptions 1 and 3 are needed to compute the OLS estimators in the first place. That is, we cannot even compute them if assumptions 1 and 3 are not true. We will see that for statistical property 1 of the unbiasedness that we will describe in the next section, we need assumptions 2, 4, and 5. And for statistical property 2 and 3, we'll need an additional assumption that we have described just yet, that we'll introduce later.